Let's let continuous random variable x represent the amount of time a college student needs to travel between classes at NCC. The amount of time is recorded to the nearest minute for up to a maximum of 20 minutes. Okay, this is our histogram. On the horizontal we have minutes, rounded to the nearest whole minute. So 1 minute, 2 minute, 3 minute, all the way up to 20 minutes. And this is the amount of time it takes a student to get from one class to another. So suppose a sample of students were gathered, and each student timed the amount of time it took them to get from one class to another. And the height of each rectangle represents the proportion of students that took that amount of time. So 0.01 is basically the probability or the proportion of students who took 1 minute to get to class. 0.02 is the probability or the proportion of students that it took to take 2 minutes to get to class. 0.04, the probability or the proportion of students for which it took 3 minutes to get to class. You could see the most frequent probability, 6 minutes to get to class. We have a proportion of 0.17 or 17% of the students it took 6 minutes to get to class. Okay, so if we were to add up all these probabilities, because this is a probability histogram which is based off of a probability distribution, we should get approximately 100%. There's a rectangle associated for each minute to get to class. The area of each rectangle represents the probability that the student will take X minutes to get to the next class. So the probability that a student will take, for example, 10 minutes to get to the next class is 0.06 or 6%. The probability that it will take a student's 15 minutes to get to class is 0.01 or 1%. Okay, so notice that probability is labeled on the vertical axis. What's the probability that it takes a student 10 minutes to get to class? So we go on the horizontal to 10, we look at the height, and it's 0.06. So the probability is 0.06 or 6%. The area of the rectangle for x equal 10, which is this one right here, the area of the rectangle is equal to the probability that it takes a student 10 minutes to get to class. So the area of the rectangle is width, which is 1 times 0.06, the height, so the area of the rectangle is 0.06. Area equals probability. Area of the rectangle equals probability. So what will the sum of the area of all the rectangles of this histogram equal? So if we were to add up the areas of every rectangle, just like adding up the probabilities, we should get 100%. Okay, so just like the probabilities of a probability distribution table, if we add up the area of all the rectangles, it's the same as adding up all the probabilities, which should sum to 100%. The probability a student will require from 5 to 7 minutes to get to the next class is equal to the sum of the areas corresponding to the shaded rectangles associated with x equal 5, x equals 6, and x equals 7 minutes. So if we take the areas for x equal 5, 0.12, plus 0.17, plus 0.16, because remember the area is the same as the probability. The area of the three rectangles is the sum of their probabilities, and therefore the probability that it will take a student from 5 to 7 minutes to get to class is the sum of those three rectangles, which is 0.45 or 45%. Okay. So let's take a step back, because we've been measuring time to get to class, but we should recognize that time is a continuous random variable. Time is not discrete. So we rounded, those students that measured their time to get to the next class rounded to the nearest whole minute, but in reality, time is not something that is discrete. So what if instead of rounding to the nearest minute, we rounded to the nearest quarter of a minute? Okay? For example, 5.25 or 5.5 or 5.75 instead of just either 5 or 6. So we got a finer degree of measurement now. Look what happens. We have more rectangles. More rectangles for a finer degree of measurement. Okay, so instead of, let's see, here's 5. Okay, instead of just 5 and then 6, we have 5, 5.25, 5.5, 5.75, and then 6. Okay, and what if we were to do this even to an even finer degree of measure? What if we were to measure this to the nearest tenth of a minute? We're still going to recognize that no matter how close we make our rectangles, the sum of all the probabilities will still be 100%. Okay, so if we were to add up all of these rectangles all over again, the sum is still going to be exactly 100%. That's just the rule of a probability distribution. So if we were interested in finding the probability that it takes a student between 4.5 and 7.5 minutes to get to class, okay, here's 4.5 approximately right here, and 7.5 is approximately right here. So if we were trying to find the probability that it takes a student between 4.5 and 7.5 minutes to get to class, we simply add up the probabilities for all the rectangles between 4.5 and 7.5. The probabilities of the rectangles are the areas of the rectangles. So the probability of this event happening is the area right here. Okay, now let's go back to that issue I had brought up earlier. What happens if we measure to an even finer degree? 1/100th of a minute, 1/1000th of a minute. So our rectangles now on the horizontal axis are shrinking in size. The rectangles are going to get skinnier and skinnier and skinnier. They're going to get more frequent. We're going to have many more rectangles. They're going to be much narrower and eventually going to take on the appearance of a smooth bell curve. This is called the probability density curve. We call it a curve because there's no more rectangles anymore. It's a smooth curve. However, no matter what, the area under the curve, just like the sum of the area of all the rectangles, is still 100%. Okay, the area under the probability density curve between two possible values of the continuous variable represents the probability that the value of the continuous variable will fall between these two values. So if we were asked to find the probability that it takes a student between 5 and 7 minutes to get to class, just like with rectangles, the probability of that event happening is the sum of the area underneath the probability density curve between 5 and 7. Okay, so this area underneath the curve between 5 and 7 is the probability that it takes a student between 5 and 7 minutes to get to class. We don't see rectangles anymore, so it's kind of hard to figure out what the area is. Okay, so if we don't have rectangles, how can we figure out area under a shape like this? Well, that's actually a calculus question. If you've studied calculus before, you know that you can find the area under curves using integration. If you haven't taken calculus before, it's fine, because we are not going to use calculus to do these problems. We're going to be using our calculator. Okay, so this area represents the probability that it will take a student from 5 to 7 minutes to get to class. The probability that a continuous